My name is Dariush Salami. I'm a PhD candidate at the Department of Communications and Networking at Aalto University. I'm going to present PointGest motion pattern recognition in 4D point clouds paper, which is accepted in the Machine Learning for Signal Processing or MLSP 2020 conference. I've done this work together with Samira Palipana, Manila Kodeli, and my supervisor Stefan Zek. There is a wide range of applications in which computers should interact with their surrounding environment, especially humans, through different sensors. Human robot interaction, human vehicle interaction, and sign language detection are a few examples of these applications. A great variety of these sensors generate point clouds that are unordered sets of points in the 3D space, unlike pixels in images. So, there is a need for processing 4D or dynamic point clouds. There are different ways of processing point clouds in the literature. A few methods require a time and memory consuming preprocessing named voxelization. These methods convert the point clouds into grids called voxels that are equivalent to pixels in the 3D space. Then they use conventional image processing techniques like convolutional neural networks or CNNs to process these voxels further. Apart from the computational complexity and memory consumption, this approach loses some information as it's shown in the picture. Another group of approaches projects point clouds over different planes. They then render different views of the point cloud on those planes and use the standard image processing techniques as mentioned before. These approaches are also computationally expensive since they need to process different views. Moreover, we have still the information loss here. Finally, another group of methods directly consumes the point clouds and extract features without doing any pre-processing. So, these methods are not lossy and they preserve all the information in the point clouds. PointGest is a neural network architecture that directly consumes 4D or dynamic point clouds. PointGest is designed in the way that it can extract not only spatial features but also temporal features of the input point cloud. Let's see how it works. First of all, PointGest extracts spatial features of the input frames through PointNet++ blocks. These blocks share their weights to decrease the number of trainable parameters of the network and as a result increase the generalizability while reducing the chance of overfitting. The internal architecture of these PointNet++ blocks is shown in the left figure. These blocks have two set abstraction layers. Each set abstraction layer samples the points using farthest point sampling algorithm, then utilizes the bulk query algorithm to build the local regions. Finally, it uses PointNet components to reduce the number of points. After applying two set abstraction layers, a fully connected layer is applied to calculate the final spatial representation of the input frame. In the following part of the model, we have a couple of long short-term memory or LSTM layers to extract the point cloud's temporal features by processing the latent feature vector of each layer containing its spatial characteristics. Finally, in the last part of the model, we use a couple of fully connected layers with dropout layers to extract the fine-grained features. The dropout layers are responsible for reducing the variance of the model by introducing noise. The last layer of PointGest is a fully connected layer with C neurons and without any activation functions to calculate the class scores. C is the number of classes of the dataset. To evaluate the model's performance, we use the Upper Body Point Cloud Gestures dataset or UBPG. This dataset has 10 classes of gestures shown on the screen. You can see the temporal progress of the gestures on the screen in 4 consequent frames. The 0 class is no gesture. Some of the gestures in this class are a person with no movements, and the rest are a few random gestures that do not belong to the other classes. The dataset is collected from 6 participants using an MS Kinect device. There are 142,000 frames from almost 4,000 videos, and the dataset is a collection of dense 40 point clouds. In each frame, we have between 1,000 to even more than 10,000 points, and each gesture has a different number of frames. To reduce and also fix the number of points and frames, we uniformly sample them. The effect of the number of points and frames are evaluated and will be discussed in the following slides. We've defined 5 settings on the dataset, 3 of which are the same settings in the baseline paper or FlickrNet, and the rest are new settings with the latest version of the dataset. The information about each setting is shown in this table. The first setting has only one user, setting 2 and 3 have 5 users, and finally, the last 2 settings contain 6 users. To evaluate the model's generalizability on the unseen participants, we have done subject-dependent data split in settings 3 with either 5 or 6 users. The comparison of the state-of-the-art models and PointGest is shown in this chart. ONH consumes voxels, but the rest of the model consume point clouds. Furthermore, PointNet and PointNet++ models treat the gesture recognition task as a 3D shape classification task. Since they cannot explicitly model the temporal dependency in the data, we simply aggregate the gestures through time and feed them as a 3D point cloud to these two models. We didn't have either the code or the implementation details for some models, unfortunately. So the missing bars represent the models that are not evaluated in some settings. As you see, PointGest outperforms all the models in all the settings with 1 and 5 users. There are 1, 3.5, and 7.6 accuracy improvements on settings 1 to 3 respectively. As mentioned before, we've also evaluated the available models and PointGest on the settings with 6 users. As it's shown in this chart, PointGest outperformed the closest competitor with a margin of 5.4 and 8.6 in subject independent and subject dependent settings. The reason behind the drop in the accuracy from setting 2 to the setting 3 could be the lack of training data. As it was shown in previous slides, we have much less training data in setting 3 than setting 2. Apart from that, since the setting 3 is a subject dependent split, the results suggest that the style of making the gestures among the training and the testing users is different. In this slide, we have the 3 confusion matrices for the settings with 5 users. In setting 1, we have conflicts in the instances of the first 2 classes that could be again because of the lack of the training data. The amount of the training data in this setting was 1/2 of the rest of the settings. In setting 2, 9 out of 10 classes of gestures have more than 98% accuracy, and we see no notable confusion. In setting 3, we have a few conflicts. For example, gestures with label 6, 8, and 9 are both handed, and the gestures with label 2 to 5 all are one handed. These observations suggest that the gestures with the same number of hands involved in the process are more prone to conflict. Moreover, we do not have these conflicts in setting 2. So it shows that the style of making gestures is essential in this setting since we have a subject dependent split here. So the users who are in the testing set are not used in the training phase of the model. We also analyze the effect of the number of frames and the effect of the number of points in each frame on the overall accuracy of the system. The results suggest that both the number of frames and the number of points in each frame play important roles in the model. As shown in the figure, for a gesture with 32 points, by increasing the number of frames from 2 to 8, we obtain a 29% gain in the accuracy. On the other hand, for a gesture with 8 frames, We can improve the accuracy by 16% if we increase the number of points in each frame from 32 to 1024. There is another interesting point in the figure. By decreasing the number of points from 1024 to 128, which is almost one tenth of the input size, we only observe 1%, 3%, and again 1% drop in the data with different number of frames. Let's even consider a very strict scenario. By reducing the number of points from 1024 to 32, which is almost 97% of the input size, we only lose 16% accuracy. These results suggest that the model is highly resilient to the missing points. But what's the reason behind that? We will discuss it in the next slide. Here, we visualize the points that are contributing to the last max spelling layer in each PointNet++ blocks. We call them critical points. You can see that although we feed 1024 points to the network, only a small fraction of them, something between 200 and 250, define the max spelling layer's output, the output on which the temporal feature extraction is being done. So, this makes the model highly resilient to the missing points. To find these critical points, we repeat one arbitrary point of the input point cloud 1024 times and remove the remaining points in each frame. Then we bring the removed points back one by one so that we replace it with one of those repeated arbitrary points and measure the last max spelling layer's output in each frame. Points that improve the last max spelling layer's output are considered as critical points. To wrap up the presentation, we summarize the most important points in the paper. We propose a neural network architecture called PointGest to directly consume 40-point clouds to recognize gestures. We showed that PointGest outperformed the state-of-the-art models in 5 different settings with either subject-dependent or subject-independent data splits. We also analyzed the effect of the number of frames and the effect of the number of points in each frame on the overall accuracy of the system. And we visualized the critical point clouds to show that the model is highly resilient to the missing points. Thank you so much for your attention. Is there any questions?